Hi everyone. In this, our third look at the Laplace transform, we are going to transform functions of the form f of t equals t to the n. We will start by using the integral definition of the Laplace transform to transform the function f of t equals t. Then I'll show you a shortcut that allows us to get all of the rest, essentially using algebra. We will wrap up with an example of using the Laplace transform to solve a differential equation. All right, so let's start with this one. We are going to transform t. So f of t equals t is our first function. Just to revisit the integral definition of the Laplace transform, it's an improper integral. I'm going to go ahead and switch this into computational form. So we will write the limit as b goes to infinity of the integral from 0 to b. The integrand is e to the negative st times t dt. All right, so normally you write the integral from 0 to infinity, and then you bring in this notation. So I just jumped straight to that form. This is the product of two functions, and the exponential function doesn't get better or worse after differentiation or anti-differentiation. However, if we differentiate t, we go down to 1. So let's do integration by parts, where we will let u be t, so that du is 1 dt. dv will be the rest of it, so e to the negative st dt. Well, I don't know why I'm writing it up there. All right, so I just dropped all my markers, had to cut away for a second, but we'll have e to the negative st dt. That means v should be e to the negative st times negative 1 over s. Okay, let's switch this over now using integration by parts. With integration by parts, you're not changing variables. There's no bounds to change or anything like that. With u substitution, it's just a way to rearrange this integral in terms of other expressions. So we'll have the limit as b goes to infinity of u times v, so negative t over s, e to the negative st, evaluate that from 0 to b, minus the integral of v du. We are anti-differentiating with respect to t. We can treat s like a constant. So what I'm going to do is pull this negative 1 over s in front of the integral that I'm about to write down. Minus negative 1 over s is plus 1 over s. And then integrate from 0 to b, e to the negative st dt. Like that. All right, let's plug b in now for t. Be careful. We have t and s, but we've anti-differentiated with respect to t. So now to evaluate this, we'll put b and 0 in for t. All right, so we'll have negative b over s, e to the negative sb. When I plug 0 in for t in the second term, it just goes away because of this, plus 0. And then here I need to anti-differentiate, so we'll have plus 1 over s times the antiderivative of e to the negative st, which is negative 1 over s e to the negative st. Evaluate that from 0 to b. Okay, we could go ahead and evaluate this, but I think I'll just rewrite the whole thing so that we can plug in these bounds, and then we will evaluate the whole expression as b goes to infinity. So this is going to be the limit as b goes to infinity of this part, so negative b over s e to the negative st minus 1 over s squared, and then let me plug this in, and I'll write e to the negative sb minus e to the 0, which is 1. All right. I have a little mistake here. Should have written b. Okay, there we go. Let's pause for a second and analyze this expression as b goes to infinity. All right, we've seen this argument a couple of times. We have this exponential term e to the negative sb. If s is positive, negative s is negative, and then b is going to infinity. So this expression here that we're raising e to goes to negative infinity, which means this exponential term goes to 0 whenever s is positive. That's the same story here, in fact, so we're doing two terms at the same time. When s is 0, these denominators are 0, so s won't be 0. And then if s is negative, negative s is positive. So this would be a positive number times something going to infinity, and that's going to be the exponential growth side of the exponential function. So there the limits would not converge. So this limit only has a chance if s is positive. We have a little bit more going on, though, because we have this b in the numerator here. The exponential is going to win when we compare b going to infinity and e to the negative sb going to 0. But let me save the argument for a minute. I'll come back and do L'Hopital's rule after we finish this computation, just to verify that. So if you can accept this for now, with justification in a few minutes, this expression goes to 0 if s is positive, otherwise it diverges. Exact same story here, except we don't have to worry about a leading coefficient of b. This piece also goes to 0 when s is positive, otherwise it diverges. Okay. So if s is positive, this goes to 0, this goes to 0, this is just 1. So that overall this limit is going to be just this times 1. Actually, it's negative 1 over s squared times negative 1. Overall, it's 1 over s squared. And in order to say that this existed, we needed s greater than 0. All right, that's the end of my computation. I'm going to step away so that you can finish writing this down if you're doing that. Then I will come back in a minute, just in case you'd like to see it, and justify that this product goes to 0 when s is positive. All right, just to give you the complete argument, I want to revisit this term using L'Hopital's rule in case you didn't see how to do that. Let's switch from b to x, and I'm going to imagine that this is a nice, it's actually a differentiable function of x of the form negative x over s e to the negative sx. We're going to take the limit of this as x goes to infinity. I'm going to rearrange this as the limit as x goes to infinity of just 1 over s, that's a number, x, actually let me put the negative sign there, x over e to the sx. Okay, because that negative exponent there can flip down to a denominator. This is going to infinity. This is going to infinity when s is positive, so that this is an indeterminate form. We just need one round of L'Hopital's rule to see this. I take the limit as x goes to infinity of negative 1 over s, just hangs out front. Differentiate the top with respect to x and you get 1. Differentiate the bottom with respect to x and you get s e to the sx. And now as x goes to infinity, if s is positive, this is going to infinity, so overall this goes to 0. Now I would like to show you the shortcut. This will work for t to the n for any integer n greater than or equal to 1, including the example we just did. This is going to use the identity that relates the Laplace transform of a function and the Laplace transform of its derivative. So here's the function we're going to look at. Let y of t be t to the n. That's what we want to transform. Therefore, dy dt is n t to the n minus 1. And also the other piece of information we will need for that identity is what y of 0 is, but y of 0 is 0 to the n. So let me just make a note here that y of 0 is 0. That's nice. Okay, let me start plugging this information into that identity. We will need that the Laplace transform of dy dt is equal to s times the Laplace transform of y minus y of 0. This is the identity that we're going to use. Let me switch markers. Okay, so on the left-hand side, I'm going to write Laplace transform of n t to the n minus 1 is equal to s times the Laplace transform of t to the n, and then minus 0. I'm going to write this one more time. I'm going to solve for this Laplace transform. The idea is this is for t to the n, and the Laplace transform on the left-hand side is involving t to the n minus 1, where that's 1 power lower. We're actually going to build up through powers of n. You'll see what I mean. So that didn't immediately click with you. Just hold on for a second. Let me solve for this. The Laplace transform of t to the n is 1 over s times the Laplace transform of the derivative nt to the n minus 1. N here is actually just a constant. So using the linearity, we can take this n and pull it out so that, I'm going to write it over here, the Laplace transform of t to the n is n over s times the Laplace transform of t to the n minus 1. Okay, let's just write out the first few powers of t. So in particular, what does it look like if n equals 1? Then we have the Laplace transform of t, which we just found, equals 1 over s times the Laplace transform of 1, which I computed using the integral definition back in the first video. You could also use the exponential formula that we had in the second video, setting that constant a equal to 0. That should do it for you. Regardless of the method, this Laplace transform is 1 over s. So we have 1 over s times 1 over s is 1 over s squared, picking up the same domain as the Laplace transform of 1, so we know that s is positive. And that's what we just found. Okay, but let's move up now to n equals 2. The Laplace transform of t squared is n over s. So in this situation, that's 2 over s times the Laplace transform of t. We just found that. That's 1 over s squared. So we'll have 2 times 1 over s cubed, and I do want to write it that way, even if the numerator seems a little silly. So 2 times 1 over s cubed. Pause for a second. Go ahead and write out the Laplace transform of t cubed. Okay, following this pattern, if n equals 3, we have the Laplace transform of t cubed. That's going to be 3 over s times the Laplace transform of t squared. We just wrote that down. So again, I'm going to write the numerator in factored form. 3 times 2 times 1 over s to the 4th. By now you probably see the pattern, but let's just do it one more time for n equals 4. I'll do this a little bit differently. The Laplace transform of t to the 4th is 4 over s. Let me go ahead and write this here. Times 3 times 2 times 1 over s to the 4th. And now for that numerator, I'm going to write an expression you're probably anticipating, which is 4 factorial, all over s to the 5th. So 4 factorial means 4 times 3 times 2 times 1. I think by now we've spotted the pattern. So for general n, the Laplace transform of t to the n Okay, let's compare numbers here. 4 was 4 factorial, 3 was 3 factorial, 2 was 2 factorial. So the numerator should be n factorial. And then for the denominator, when n was 4, it was s to the 5th. When n was 3, it was s to the 4th. When n was 2, it was s cubed. So it should be s to the n plus 1. I stopped writing the domain, but it's always going to be the same as what we started with, which is positive s. Let's wrap up this lesson by using the Laplace transform to solve this first-order ordinary differential equation, dy dt equals 2y plus t squared, with an initial condition that when t equals 0, y equals 1. So we are going to use the Laplace transform to find the Laplace transform of y, the unknown function which solves this initial value problem. And then knowing the Laplace transform of y ultimately will tell us what y should have been. So along the way, we'll use all three of these facts. We'll use the first one right away, because we are going to take the Laplace transform of both sides of this differential equation. On the left, we have the Laplace transform of the derivative of this function we're looking for, so dy dt. And on the right-hand side, we have the Laplace transform of 2y plus t squared. Okay. From this first fact, the left-hand side can be written as s times the Laplace transform of the function we're looking for, minus, let me write y of 0, but we actually have that information. We know that's 1. So I'll start with y of 0, and on the next line, when I arrive at that term, we will write 1 instead. On the right-hand side, we're going to use linearity. So I'm going to break this sum up into the Laplace transform of 2y plus the Laplace transform of t squared, and I will also go ahead and pull that 2 out front, so that's also part of the linearity property. All that to say that the right-hand side is going to turn into 2 times the Laplace transform of y plus the Laplace transform of t squared. Let's now try to isolate the Laplace transform of y. It's basically turning this differential equation into an algebra one. So we're going to isolate the Laplace transform of y like it's a variable. Okay, so I'll bring this over. Go ahead and factor out Laplace transform of y so that we can write s minus 2 times the Laplace transform of y on the left-hand side. And then over here, let me write the Laplace transform of t squared first. We know that's 2 factorial, which is 2, divided by s cubed, and then plus y evaluated at t equals 0, but we know from what we were given that that is 1. Okay, we keep going with our request to isolate the Laplace transform of y. The Laplace transform of y is 2, this is the bad part of doing this, 2 divided by s cubed times s minus 2 plus 1 divided by s minus 2. Okay, I said bad part. You might not have realized what I was talking about, but let me tell you now. This expression looks good if I'm trying to recognize that a Laplace transform has occurred. So this expression, 1 over s minus 2, looks like the second fact here. This looks like the Laplace transform of e to the 2t, so that's great. But nothing up here on the right-hand side looks like the first term we have, 2 divided by s cubed times s minus 2. You run into these a lot with Laplace transforms. You need to use partial fraction decomposition. This is why we teach partial fraction decomposition in calculus. It's not that interesting otherwise, but when do you ever use partial fraction decomposition? You use it a lot when working through Laplace transform problems. So I don't know if this is fair, but I'm not going to work this out for you right now. You can go ahead and pause and work this out if you would like. And then I have videos as well where we work out partial fractions. I'm just going to write down what the decomposition is in a minute. What do you need to do, though, is we need to take this denominator and make what should actually be 4 terms in our decomposition. 1 for s minus 2, okay, that's fine. And then 1 for s squared, and 1 for s cubed. So if you remember that about partial fraction decomposition, when you have a power like this, you have to account for every factor in that power. So s squared, and s cubed. Okay, go ahead and try to work this one out, and then I will come back and tell you what the partial fraction decomposition of 2 over s cubed minus s cubed times s minus 2 is. All right, here's the solution. I'm going to keep writing to the right here, otherwise we might run out of room. When I do the partial fraction decomposition for this term, I need to have a denominator that looks like s minus 2, I'll do that one first, with a denominator that looks like s squared, and s cubed. Then let me go ahead and write plus 1 over s minus 2. Okay. Here, your numerator would be a constant, here a constant, here a constant, and here a constant. You might think I would need like ax plus b, but actually you don't. So that's the good news whenever you have this kind of repeated factor term. All right, so what do these constant numerators look like if you work out the system of equations? For this one, I have it written down here, it's 1/4. For this one, plain old s, it's also, well, it's actually negative 1/4. For s squared, it's going to be negative 1/2. And for s cubed, it's going to be negative 1. Okay, so that's the partial fraction decomposition of this first rational expression here. I recommend doing what I've done here and writing something like a fraction in the numerator instead of writing 1 over 4 times s minus 2 or 1 over 4s minus 8, because you want to recognize this denominator as belonging to the second piece. And it's easier to see if the denominators have the same denominators that we see here. So any kind of constant like 12 over 17, I would keep it entirely together in the numerator or out front, but I wouldn't bring those constants into the denominator. Okay, let me come down here now, and before we start inverting the Laplace transform to find y, let me, actually, you know what? I'm going to just go ahead and add these together right here. So 1/4 plus 1 is 5/4. So let me just change this to a 5. And that will save us rewriting this whole expression. Okay. All right, now it's a question of recognizing what you would have taken the Laplace transform of to get each of these 4 expressions. So I want to realize that this expression looks like the Laplace transform of something. I need to find what that something is. So there is no like recipe for recognizing Laplace transforms except to just know them and do a lot of practice so that you start to recognize familiar pieces. Okay, so this looks like 5/4 times 1 over s minus 2. And 1 over s minus 2, because of the second identity, is the Laplace transform of e to the 2t. So I will write, how about I leave the 5/4 out front? It's 5/4 times the Laplace transform of e to the 2t. What about negative 1/4 over s? I didn't have space up here to write the Laplace transform of just plain old 1, but you can actually get that from either second or third line. So if you let a equals 0 in the second line, e to the 0t is 1. So the Laplace transform of e to the at when a equals 0 is the Laplace transform of 1. So we know it's 1 over s. I'm like, okay, when I see a denominator that's just s, I know I'm looking at a constant. So 1 over s is the Laplace transform of 1. Let me write negative 1/4 times the Laplace transform of 1. Right, so that's that second term. Then this is going to look like t, and this one like t squared, except that the numerators might not match the n factorial expressions. You can either try to do a balancing act here. Maybe I'll do that for this third one. The Laplace transform of t is 1 over s squared, so I don't think we need to do any special design here. Let's just write negative 1/2 out front times the Laplace transform of t. So that goes with the s squared. So here, here, and here. Now we're left with s cubed as a denominator, which we recognize should pair up with t squared, t squared. Yeah, t squared. Sorry, I'm like s cubed, t squared. Got to get your powers the direction you go correct. However, were I to take the Laplace transform of t squared, I would have a factor of 2 in the numerator because it should be 2 factorial divided by s cubed. So you don't have to do what I'm about to do, but it might be a safe thing to do. And that is to take this 1 here and write it as 1/2 times 2. The 1/2 we'll treat like we treated these other constants. That will just stay in front. But now 2 over s cubed looks like the Laplace transform of t squared. Okay, so we'll have minus 1/2 times the Laplace transform of t squared. And that is all 4 terms. All right, Laplace transform is linear. So for each of these expressions, I can now bring the constants inside. This first expression is equivalent to the Laplace transform of 5/4 e to the 2t. Similarly, this is, if I take this whole thing, including the sign here, this expression is equivalent to the Laplace transform of negative 1/4. This whole expression, including the sign, is equivalent to the Laplace transform of negative t over 2, and this one, negative t squared over 2. All right, so you could bring the constants inside, and then you could take like the sum and difference of individual Laplace transforms and just make them one gigantic Laplace transform. So this tells us now that we're looking at the form of t. What we're going to do is say that the Laplace transform of y, the unknown solution to this differential equation that we're trying to solve for, is equal to one big Laplace transform on the right-hand side, and it's the Laplace transform of 5/4 e to the 2t minus 1/4 minus t over 2 minus t squared over 2. This is one gigantic Laplace transform if I put it all together using linearity. But for a continuous function like y, it's a solution to this differential equation, the Laplace transform is invertible. So if the Laplace transform of this equals this, the Laplace transform of this, that means that what we took the Laplace transform of had to be the same thing. So the solution to our differential equation is y equals 5/4 e to the 2t minus 1/4 minus t over 2 minus t squared over 2. What I think is really fun about the Laplace transform, or just really neat, is that you take a differential equation involving derivatives, you think of, rates of change, and turn it into an algebra problem to solve. We turned it into just an equation for an unknown variable, Laplace transform of y. And then yes, partial fractions isn't necessarily fun, but I always feel like I'm a detective trying to solve a mystery when I work through these problems. I don't know, I just think it's really cool. So hopefully you enjoyed working through this example, at least getting to this final form, even if this step maybe wasn't so pleasant. Again, we will do more examples of these over the next several videos.